Thank you, Stan. This morning I would like to talk about how behavioral finance can be used to monetize from errors that market participants make, and in particular how machine learning is a powerful tool in exploiting these kind of opportunities. There are several reasons why machine learning is a good tool in combination with behavioral finance. Number one, behavioral finance data sets are complex. They are unstructured. They require very specific tools in order to unfold what is the complexity and analyze the information that is contained in those series. You can think of social media, you can think of the Internet of Things. Number two, more generally, we need an objective definition of what is a behavioral bias, in the sense that a bias is defined against the outcome that would have come from a decision maker who is not subject to those psychological traits. And let me read here a quote from Professor Kahneman, who said, "It is very difficult to imagine that with sufficient data, there will remain things that only humans can do. One thing that I find extraordinarily surprising and interesting in what is happening with AI these days is that everything is happening faster than expected." I guess he had some behavioral finance or some expectations that were not fulfilled in this case. He added, "You should replace humans with algorithms whenever possible. Even when the algorithms don't do well, humans do so poorly and are so noisy that just by removing the noise, you can do better than people." Now the question is, how can we utilize these tools in practice? And this morning, Professor Barberis described three different biases that are affecting investors. And what I'm going to do now is I'm going to present examples of how machine learning can be utilized in exploiting each of these biases. So let me start with textual sentiment analysis. Textual sentiment analysis can be utilized to model the overconfidence of market participants. So you can think of various sources of information that are available to market participants. This would include sentiment expressed by corporations, like public filings, 10-Ks, 10-Qs. You can think of press releases, conference calls, transcripts. At the same time, a lot of the information that is available to the public comes from the media. News articles, analyst reports, sell-side analysis. And the third kind is sentiment expressed by the general public. Internet blogs, social media. Traditionally, these texts have been analyzed utilizing a method called bag of words. Essentially, the way this works is you would map some words to sentiment, to positive or negative connotation, and then you would just count how many words are in the text associated with positive connotations and how many words are there in the text associated with negative connotation. Now, as you can imagine, that's rather rudimentary and is not particularly accurate, but it's still, when you play the game of numbers, it can provide you insight into whether the market is populated by optimistic investors or pessimistic investors. A better approach is to apply machine learning techniques to understand what is the meaning of those sentences, what is the context. One way to do this is to have a human label manually sentences. So you're given the following task. Considering this sentence, would you associate it with a positive connotation or a negative connotation? And you do that for thousands and thousands of sentences. Then the machine learning algorithm is going to identify the patterns that are associated with sentences that have a positive connotation. And remember, we are not teaching the algorithm to recognize what makes this sentence positive. The algorithm will learn it itself. That's the learning component of machine learning. A machine learning algorithm learns the structure of the data without us directly being involved in the learning process. We're just providing examples. Once you provide a training set, then you have to evaluate the quality of the forecast against a testing set. And you do that with various model specifications. Over millions of trials, the algorithm eventually learns to characterize what makes a sentence positive or negative. And then you collect the sentiment of the various sentences within a text, and in this way you have the sentiment of the text. Let me show you an example that you can find in your Bloomberg terminal today. Bloomberg is already evaluating the sentiment of text associated with every major stock. So in this case, what you can find here is for the stock prices of Tesla, Bloomberg is collecting thousands of news articles per day, and every day it evaluates whether the articles are positive or negative. What happens when there is an imbalance, a negative imbalance in sentiment? Well, typically it's followed by a negative trend. Over time, maybe there is here like a positive imbalance that eventually stops the fall and starts a new rally, right? Essentially, you can see how sentiment, this overconfidence of investors, eventually causes a trend. And that's something that you can find also when perhaps the sentiment is not in balance, but there are a lot of contradicting sentiments. That's typically preceded by a period of high volatility. So not only sentiment imbalance is helpful in predicting trends, but it's also helpful in predicting volatility and increasing risk. Let's look at the second example. Rather than news articles, now we're going to look into tweets. This is the same layout. We have here the price of Tesla. Now we have the tweet volume, right? You can find tremendous amount of tweets, sometimes over 20,000 tweets, including the code for Tesla on any given day. And here you can see the imbalance, right? The imbalance, it has the same reading. Positive imbalance, positive trend, negative imbalance, negative trend. And these little birds are the infamous tweets by Tesla's courageous leader. Now, something that might be striking to you is that whereas here the volume of the news articles is reflected in the positive or negative bias, here you can see that there are very high bars, even though sometimes there is very few texts classified as positive or negative. And the reason is this. It is much harder to extract sentiment from a tweet than from a text. And to us humans, that might sound strange, because typically tweets can be very impulsive. And people try to express and perhaps even exaggerate the sentiment within the few words that are available in the text. But to the algorithm, that's hard, because there is a very different tweeting style, if you will, between different people, which is not necessarily the case in texts. For example, you can compare a tweet coming from the residents of Buckingham Palace and a tweet coming from the residents of the White House, and you might understand why the algorithm might get confused. It's a different dictionary, it's a different kind of terms. Even the word covfefe might be very confusing to the algorithm. So that explains why sometimes you find that the numbers don't back up between tweet sentiment analysis and the number of tweets. All right, well, how would you use this? here there is a machine learning algorithm that is extracting sentiment, and this sentiment is predictive of trends, it's predictive of volatility. Moreover, you can utilize this series in combination with a second machine learning algorithm that is going to learn how to utilize this sentiment in a profitable way. Let me go now to the second example of behavioral bias that Professor Barberis mentioned. That would be over-extrapolation, greed, fear, over-extrapolation. You may remember the flash crash of May 6, 2010. Around 11:56 a.m., there was a very negative imbalance order flow. By 1:08 p.m. Eastern time, the order flow imbalance was already in the 95th percentile. It was one of the most imbalanced periods in history based in terms of order flow. By 2:32, the crash begins, and it lasts something like 3-5 minutes before it stops and then slowly recovers. So the microstructural process that was underneath this phenomenon was in fact behavioral, in the sense that what happened is, as market makers received toxic order flow and they were forced to liquidate their inventory, these market makers became liquidity consumers. And as these market makers became liquidity consumers and pressed the market further down, these injected fear in the remaining market makers. Eventually, all market makers were gone. There was nobody standing on the bid. The price collapsed 10%, and high-frequency traders kick in because, at a 10% discount, who doesn't want to be on the buy side? Now, this is a microstructural phenomenon, but what made it possible was that humans back off, pull out of the market, and what stopped the crash was cold machines bidding once the market collapsed 10%, the high-frequency traders. These machines were not biased. These machines just saw an opportunity and enter without fear, and that's why we talk today about a flash crash as opposed to a 1987 style crash. Well, there are ways of measuring this kind of exponential patterns in the markets. One example I'm going to show you today is something called an SIDF model. An SIDF test is essentially a right side test on the unit root of a process, which essentially stands for when prices are moving exponentially, whether exponentially up or exponentially down, this test is going to recognize the presence of this sort of feedback loop mechanism operating. How common are exponential patterns? Very common. You can see it here. This is the flash crash. It was not even the most exponential pattern that we have observed in history. This is the pattern of August 20th, 2015, which was caused by a conjunction of routes in emerging market assets. And now, what we can appreciate is that actually they are quite common. It's very common for markets to experience this sort of exponential bubble-like behavior. And what is behind this behavior is, like in the flash crash, these sort of behavioral biases: fear, greed. And machines can be helpful in identifying when a human is making a mistake based on this fear and greed. And that's why the second application is to utilize this sort of series in conjunction with machine learning algorithms to learn how to respond to episodes of fear and greed. Third and final example that Professor Barberis mentioned was prospect theory. And in particular here, I'm going to discuss probability neglect. What is probability neglect? Well, in the definition that Kahneman uses in his book is that humans are particularly bad at differentiating between events with high and low probabilities. So for instance, perhaps your relatives ask you to give them a call as soon as the plane lands, but they don't ask you to give them a call as soon as you get out of the cab, even though the probability of dying in a traffic accident is 1 in 5,000, and the probability of dying in an airplane crash is something like 1 in 11 million. Well, let's make an example that is related to finance. Consider a poker game, like No Limit Texas Hold'em. Cards are randomly distributed. The player's goal is to estimate the relative strength of his or her cards against the other players. When a player holds a strong hand, she may assume that other players hold weaker hands. There are even some people who count cards in order to evaluate that probability, which is considered against the rules. The estimated relative strength informs the key decision each player has control over, bet sizing. And that's really what makes a good poker player. A good poker player is the player who is able to size the bets properly. The cards are distributed randomly. Really, the decision is to figure out when you have an advantage and when you should go big in order to try to bankrupt your opponent. To some extent, this is something similar to what happens in financial markets. The key decision an investor can make is sizing bets properly. The bet could be 0 if you want to be out of the market, or it could be big if you feel that you have enough information. In fact, an informational asymmetry, something that other people don't know. This relates to overconfidence, but right now we are talking about probability of neglect. Now, consider an investment strategy with a precision of 60% and a recall of 90%. That means that whenever you make a prediction, 60% of probability that the prediction is going to be right. And the number of opportunities available are about 90% of the opportunities that you take advantage of. Now, if this strategy identifies 90 out of 100 opportunities, and it makes money 6 out of 100 identified opportunities, you would expect that this strategy makes money. But that's not necessarily the case. Why? Because it is entirely possible that the strategy bets big on the false positives, and it bets small on the true positives, right? So bet sizing is key. You can have an algorithm that predicts prices accurately, but if it predicts prices with the wrong confidence, right? Even if the sign is correct, but the confidence associated gets it backwards, you can end up losing money. What is the solution to this, especially given that humans are so bad at bet sizing? Well, it's to utilize a machine learning algorithm that learns how to use those predictions. And that's called meta-labeling. Let me describe in detail how meta-labeling works. Suppose that you have a model for making predictions. It can be a fundamental model. It can be a model based on theory. What this model tells you whether the market is, a price is above fair value or below fair value. And now the question that remains to be answered is how much should we invest in a particular opportunity? And rather than us humans making the wrong call, what we could do is we could fit a machine learning algorithm based on the outcomes from previous predictions. Remember that this algorithm is not predicting whether the price will go up or down. This machine learning algorithm is predicting whether the other prediction, the prediction from the primary model, is going to be successful or not. So the machine learning algorithm is not trying to override the decision of the primary algorithm. It's just trying to predict whether the first algorithm is going to be successful or not. And you can use that information to derive what are the bet sizes that allow you to maximize a combination of precision and recall. Essentially, what will happen is the algorithm is going to give up some recall, is going to stay home for some opportunities, and then it's going to concentrate the investment risk to the opportunities that it deems most successful. So essentially what it's doing is transferring some recall into precision. And by filtering out the false positives, it allows you to achieve a higher Sharpe ratio. So that's the third application I wanted to discuss. We have some time left, and please ask me any questions that you feel are pertinent. Thanks. Yes.
Hi, thanks for a fascinating talk. Very, very interesting. I'm intrigued by something which in control theory and electrical engineering we call the aliasing phenomenon. Mm-hmm. You showed us a lot of frequency on data on tweets, data on machine learning, and also the frequency of stock prices. So one thing we know by looking at those things, that the frequency that you estimate in affects the parameters, and you cannot apply standard tests like SIDF without adjusting for it because the parametric statistics don't work. So how do you take care of the fact, just like in currencies, I'll give you an example, when you sample at a minute frequency or 1/100th of a minute frequency, and then you look at the volatilities, do you get long memory processes? Do you get
Yes.
Feigarts processes? How do you correct for those things? Because I don't see that happening here. Maybe I'm confused.
Yeah, that's a great question. And there are two important phenomena here at play in your question. One is whether the process is stationary, right? Stationarity means that observations are comparable. So for instance, the dogs of cats are stationary, right? Because cats don't evolve fast enough so that the face of a cat is completely different from the face of another cat. Evolution is not that fast. So the faces of cats are stationary. At the same time, there is another important phenomenon that you're describing, and that's memory. And memory is important because memory is what allows us to predict things. Memory is essentially the correlation between past observations and future behavior, right? So in the case of faces of cats, they have a very high memory because, again, you have parents and children, and the children inherit the traits of the parents. Now, what I describe now involves non-stationary series. Prices are non-stationary. And you're right that we need to deal with the non-stationarity. Now, in order to deal with the non-stationarity, the typical transformation that an econometrician would do was to apply differences. The problem of applying differences is that they remove some memory. And memory is precisely what we needed to make forecasts. So how can we address this conflict between having comparable observations and at the same time retaining some memory? And the answer is something called fractional differentiation. Essentially, you need to differentiate just as little as you need in order to achieve stationarity while preserving as much memory as you can. So that's something that's a solution, right? That's there, one way to do it. In the case of SIDF, it's interesting. The idea of SIDF as a test is that you are testing whether the series itself is non-stationary. So in the case of SIDF, you don't even need to do the differentiation because the whole point is to evaluate the non-stationarity of the process. But that's the approach that I would use. To answer your question, I would use fractional differentiation to deal with these things. Oh. Yes.
Yep. which direction the causation goes, or is this just a correlation? And if there is,
Right.
if there is some causation, are you talking about just being in front of, by milliseconds or seconds, the next guy who finally figures out what's happening? Or are you talking about something that's more structural and longer term, because it's machine learning and its ability to predict things beyond that little tiny time horizon?
Great question. And that's the debate everybody struggles with in statistics, right? Correlation versus causation. Think about how this problem is answered by econometric analysis. The idea is we feed a model where we're trying to explain the variance of a y variable as a linear combination of x variables. And the idea of this adjudication is that because you have this linear additive representation, you apply an argument called ceteris paribus, where you hold some variables constant and allow one variable to change so that you evaluate the sensitivity of y to x. And that's what we call beta, right? So that's the way econometric analysis deals with causation. It's not exactly causation, it's called inferential causation, right? We make the inference that because we hold everything as constant, we move one of the variables, we evaluate the response, the sensitivity. Machine learning has different methods for evaluating causation. The idea of machine learning is the representation is not linear, it's not additive, it's not even known. The algorithm has learned the representation. How can we evaluate causation then? Well, by randomizing variables. Let's say that I have a model that is explained by tweet, positive sentiment, negative sentiment imbalance, price reaction, and other variables. If tweet imbalance is truly predictive, if it is the cause, if it is truly predictive of market prices, what we would do is we would randomize the series of tweet imbalance, and the forecasting performance of the algorithm should decay as a result of that. So that's essentially the way machine learning deals with causation. It's called variable important analysis. Essentially, it evaluates whether a variable is involved in the mechanism that leads to a particular outcome. So that's one way. The second way is there is a very important tool in machine learning called cross-validation. In a typical statistical analysis, what we do is we take the sample and we feed the model, and we're trying to understand how y is explained by x. But that's not how machine learning works. The way machine learning works is you divide the data set into train set and test set, as I described before, and you do that for thousands, if not millions, of possible splits, and you evaluate the performance of the train set against a test set out of sample. So to answer in a sentence, the way machine learning evaluates causality is by a cross-validation of variable importance.
The shorter answer was more intelligible to me, but that doesn't mean that the other one was not right. In other words, it sounds like machine learning has all the tools in place to make sure that we're not looking at spurious relationships. Please join me in thanking Marcus for an interesting presentation.